So far in the course, we have looked at transmission lines from various angles, and transmission lines essentially involve a source at one end and a load at the other end. So effectively it looks like this. The knowledge of transmission lines is very important for multiple RF applications, but it is not the only one. Not all RF circuits consist of transmission lines. There are a lot of circuits and applications where transmission lines are not very much involved. So in those cases, the circuits or the networks in question look pretty similar to our known electrical networks. That is something like just a source and a load without a long pair of conductors in the middle. So here this is a transmission line. Here there is no transmission line. So the idea behind a simple electrical network, whether it is RF network or any other frequency network, is to ensure that the power that is coming out of the source is essentially delivered to the load 100%. Similar is the case with transmission lines. When I have a high frequency source, a wave starts traveling towards the load, and it is our aim to ensure that this wave, which is carrying some power, obviously, that reaches the load 100% and nothing comes back. So as we know, there is some reflection which may happen from the load. So our idea is that this reflected wave must be minimized. That means the reflection coefficient at the load must be made 0. So the point is, we need to ensure, whatever the case is, that the load receives the maximum power it can possibly receive. Now that maximum power could be anything. Ideally, it should be the same power as that of the source. But that never happens. Why? Because every source is not an ideal source. That is like saying the source may have some internal impedance. So in this case, let us take some source impedance case which you are already familiar with in your circuit theory courses. So let us say this is the source impedance ZS and this is the load impedance ZL. So the question now is that no matter what is the value of ZL, it can never ever reach, or it can never ever obtain 100% of the power that is generated by the source, because of this ZS element which is inside the source and will definitely consume some non-zero power. So therefore the question is, considering that the source itself, the source impedance, will consume some amount of power, in spite of that, can we ensure that the load impedance gets the maximum power that it can possibly receive, which is definitely less than the source power? Well, yes, we can definitely do that, and that is a very well known and simple answer, and that is where we have, that is the maximum power transfer theorem. And that says that the load impedance and source impedances must be complex conjugates of each other. Keep in mind, here there are no transmission lines. So that is how it is. What about this case? What happens if the source itself has some impedance? Let us say this is my source, this is ZS, and that is connected to a transmission line, and that is terminated with some load impedance ZL. And let us suppose that the transmission line has a characteristic impedance Z0. Right? So now, here in the case of the transmission line, what can we do to ensure that there are no reflections at the load? We know the condition for no reflection at the load should be that ZL must be equal to Z0. What about the source end? In the previous lecture, when we were trying to analyze transmission lines from a time domain perspective, we saw that yes, indeed, there are some reflections at the source end also. So therefore, that should definitely be considered. So what is the condition? What is the condition to ensure that there are no reflections at the source? Again, the source impedance must be equal to the characteristic impedance of the line. So therefore, to ensure that the system has no reflections, these two conditions must be met. So here, for RF circuits that consist of transmission lines, our first aim is to minimize the reflections. And by minimizing the reflections, we can hope to achieve that the load will be able to obtain maximum possible power. So this is our aim. Notice that the two are different. Now for RF applications consisting of transmission lines, in general, we can say that Z0 is real. Why? Because we are assuming that the transmission line is a lossless element, and that is a fairly good assumption. But in general, ZS and ZL need not be real. They can be real or complex, or maybe even imaginary. So in such case, the approaches are different to obtain no reflection at the source or at the load. So therefore, let us start with a very simple approach. Let us take a case where ZS and ZL are both real. ZS and ZL are both real. Now, since we are talking of two impedances, and what we saw was that the condition for no reflection at the load end and the condition for no reflection at the source end are very, very similar. So therefore, let us simplify the problem and consider only what the load end is giving us. For the time being, let's assume ZS plays no role. Let's just assume that to make our life simple. In real life, that does not always happen. But what we can say is that supposing this is a transmission line, a lossless transmission line of characteristic impedance Z0, and this is to be connected to a real load ZL. But ZL and Z0 are not equal. ZL and Z0 are not equal. So rather than saying let's assume ZS plays no role, we can say that ZS is absent, or we are not concerned about the source end for the time being. What we are interested in doing is at the load end for the time being, because both source and load ends, they have similar requirements for ensuring no reflection at either end. So the point now is that if I were to take this load and connect it across these 2 points, then because ZL and Z0 are not equal, definitely some reflection will happen, right? But we don't want that reflection. So what can we do? Well, in such case, let us try to understand what we are desirous of achieving. Suppose a wave is traveling through this transmission line. In an ideal scenario, for no reflections, it expects to see a load. It expects to see a load whose impedance is equal to Z0. Right? So in such case, what we can do is we can introduce a black box over here. Let us say this is some kind of a black box where on one side we connect our main transmission line and on the other side we connect this ZL, such that when we are looking into this black box, the impedance seen, let us say Zin of this black box, that should be equal to Z0. So therefore it ensures that there will be no reflections. But immediately we have to ensure a few things. We have to ensure a few things. We have to ensure that even if this condition is satisfied, the wave must reach this load impedance without any loss. That's like saying this black box by itself should not consume any usable power. So therefore, we must ensure that there are no lossy elements inside this black box. And what are lossy elements? For example, resistors, which dissipate power, which cannot store energy. They can only dissipate energy. So now the question is, then what should be inside this black box? And what is the function that it is doing? What it is essentially doing is that it is taking ZL from one end and it is sort of transforming it on the other end to an impedance which is equal to the characteristic impedance of the transmission line. Thereby, it is sort of tricking the transmission line into thinking that the load impedance indeed is Z0. But there is no magic over it. There is no magic. It is not merely a trick. It is indeed should try to ensure that it is merely not just tricking this transmission line, but it should also ensure that all the energy or the power goes to this load impedance. So what kind of elements can we keep? We know that Z0 is real and ZL is real. I had just used one term few minutes back, that is, this black box takes this ZL and transforms it into an impedance equal to Z0. So what are the elements that we know that can transform impedance? It's a transmission line. Can use a transmission line. So we can say that since we want to transform impedances, we know that transmission lines have this impedance transformation property, and we have seen the mathematical equivalent, which is the impedance transformation relationship. So therefore we can say that we can use this transmission line of impedance. Impedance means characteristic impedance, some Z1, right? We can use the transmission line of impedance Z1. So therefore, if the impedance on the left side is Zin, which will be equal to Z0, and the right hand side is ZL, then the impedance transformation relationship can be applied, that is Zin. Using the impedance transformation relation, we get that Zin should be equal to Z1 times ZL plus JZ1 tan beta L. Well, let us say the length is L of this Z1 transmission line. So the denominator will have Z1 plus JZL tan beta L. Now we know that Z0, Z1 and ZL should all be real. We've already established that Z0 and ZL should be real. Now even Z1 should be real. Why? Because the moment Z1 becomes complex, this would become a lossy transmission line. We want Z1 to be lossless because it has to take the energy from here and send it to the load. So therefore even Z1 must be real. So therefore, this is one expression which has both real and imaginary parts. But since the circuit elements in question are all real, we can make our life simple by trying to minimize this imaginary component. One way of doing that is to have length as 0, but then that is a very nonsensical case. That would mean there is no transmission line. So therefore, let us put this beta L, which is also the electrical length, theta, as pi by 2. Suppose we put this. Suppose we put this condition. Then in that case, how does this relation change? So then in that case, Zin is equal to Z1 times ZL plus JZ1 tan beta L divided by Z1 plus JZL tan beta L. So then in that case, if you apply the limiting case of beta L tends to pi by 2, what would essentially happen is that these two terms would disappear, and what you would get is this Z1 square by ZL. Now Zn is the impedance which must be seen by the Z0 transmission line, and therefore this must be equal to Z0, as we have already established over here. So that means, what should be the characteristic impedance of that transmission line inside the black box? That means Z1 should be nothing but the geometric mean of Z0 and ZL. Now, this is the solution, but this will happen when beta L is equal to pi by 2. So now let us try to write this down in a more rigorous manner. So beta is 2 pi by lambda times L, that is pi by 2. Now let us see then what the length of this line should be. The length of this line, this two will cancel. The length will be nothing but lambda by 4, where lambda is the wavelength of the wave that is traveling through the transmission line. So therefore, what we can do, we have this Z0 transmission line, we have this load ZL, so we can put this black box, and this black box is nothing but another transmission line of impedance Z1, which is the geometric mean of Z0 and ZL, and it should be of length lambda by 4. So this part, this transmission line, this lossless transmission line that is transforming the load impedance in such a way that over here we are seeing Z0 itself, Zin equal to Z0 is what the main line is seeing. This is called as a quarter wave transformer, or QWT. This is called as a quarter wave transformer. Now, effectively what are we doing? We are essentially having a different load impedance, but still ensuring that the reflection seen by the main line is 0 overall. So in some sense, the main line knows that even though the load impedance is not equal to its own characteristic impedance, this QWT is sort of transforming that unequal impedance of the load into Z0. So this process of minimizing reflections, even when the load and the characteristic impedance of the line are not equal, this approach is called as impedance matching. It is impedance matching. So, impedance matching is about 70 to 80% of any practicing RF engineer's job. Impedance matching is not just a topic, it is a technique that finds use in each and every RF circuit almost which exists in today's world. So, for the next few lectures, including this one, our topic of interest would be in impedance matching. What happens if the load is real? What happens if the load is complex? And what are the different ways with which we can do the impedance matching? Well, one technique we saw very easily, which we can apply for this case when both Z0 and ZL are real, that is the QWT. Now we had mentioned that whatever is the impedance transformer or whatever is the black box, that must be lossless. And what did we use? We used a transmission line of characteristic impedance Z1. And is it lossless? Definitely it is lossless, because it is just a pair of conductors. So there is hardly any place where any energy or power may be dissipated. So let us quickly note down what we have learned. Having length lambda by 4. So this comes with a drawback, that the length of this line will only work, or this QWT will only be able to match. It's a constraint, not so much of a drawback. It's a constraint that the length of this QWT must be equal to 1/4 of the wavelength of the wave that is traveling inside the line. Right? Okay. Now, is there any other way to look at it? We had said that the criteria beta L equals pi by 2 is applied. Now suppose I look at the opposite. We saw that the length must be lambda by 4. Now suppose I make the length as constant. That is some lambda 0 by 4. So now if I put this 2 pi by lambda times lambda 0 by 4, where lambda is the wavelength of the signal and that is variable, that is pi by 2. So now my question is, can I find out what are the possible lambdas for which this will be satisfied? These two will get cancelled. And these two will get cancelled. So therefore, lambda should be equal to lambda 0. Lambda should be equal to lambda 0. That means, if you look at this conversely, this QWT will be able to match only in the case when the physical length of the line corresponds to the single wavelength of a signal that is being carried. That means it will be able to match the impedance only for a wave of a unique wavelength, that is lambda 0. That means this QWT works only for a signal having a single wavelength, not for multiple wavelengths, or conversely multiple frequencies. It does not work for. The QWT works only at a single frequency. So this is very, very important, and naturally it's a drawback. In the previous lecture, we had looked at the transmission lines from a transient or a time domain perspective. Let us look at this quarter wave transformer also from a time domain perspective. Suppose we have this main transmission line of impedance Z0, and that is connected to this QWT of impedance Z1, and which is terminated with the load ZL. So again, Z0, Z1, ZL are all real. Let us go back to our initial days of learning transmission lines, and let us say this direction is the positive x-axis. Now what we are seeing is this point is essentially a junction of two transmission lines. So therefore, let us put this as the point where x is 0. So therefore, this side is the positive x-axis and this side is the negative x-axis, right? Let us assume that there is a source over here which is giving energy. Now, let us do the transient analysis of this arrangement. Let us call that this point is some AA prime, this point is some BB prime, and this point is CC prime. So let us define some quantities. For a wave to travel from here to here, from AA prime to BB prime, the time taken for a wave to travel is some T0, because it is traveling through this line Z0. Whether it is traveling this way or that way, the time taken is T0. Whereas to travel from BB prime to CC prime, either way, is T1. That means whether you are going from here to here or here to here, the time taken for the wave will be T0. And if you are going from here to here or here to here, the time taken will be T1 for a single journey. So now, suppose at time t equal to 0, some wave starts from the source. A wave starts from the source. So at what time will it reach BB prime? This is at time t equal to t0. Right? Now, what will happen? The wave is happily traveling, and then at time t equal to t0, it hits this point. Now what? What will happen? At this point, the wave is trying to cross over from a line of impedance Z0 into a line of impedance Z1. So this point will be x equals lambda by 4, because this is supposed to be a lambda by 4. Or let's not put anything over here for the time being. Let's say that this has some arbitrary length. Now coming back to our discussion in hand, when the wave strikes this point, it is essentially trying to cross a boundary from one transmission line into another transmission line. So far it was traveling in a line of impedance Z0 and is now about to cross into Z1. So what will happen is, it will see an impedance Z1. So therefore some reflection will happen, because it is now so far in Z0 and crossing into this next line but has not reached the load. It will see an impedance equal to Z1, because that is what the definition of characteristic impedance is. So let us say that this reflection coefficient is gamma 0. So what will gamma 0 be? It is the formula for load reflection coefficient, and at this point the load is Z1. So Z1 minus Z0 divided by Z1 plus Z0. Right? Now, all good. This wave has now, whatever remains of this wave after reflection is now traveling here. And then it hits point C. At what time? Time t0 plus t1. The wave reaches the load, that is Cc prime. So what will happen again? ZL is not equal to Z1. So again some reflection will happen. Let's call it as gamma L. So gamma L will be ZL minus Z1 divided by ZL plus Z1, not Z0, because Z1 is the line that is connected to the load. What will happen next? So after reflection, some of the power will be absorbed in the load and some of it will come back. Again, it will hit this boundary. It will hit this boundary. And at this boundary again it is crossing over from Z1 to Z0. So some reflection will happen. Let's call it as gamma 1. So let's say time. At what time will this come over here? The last reflection happened at t0 plus t1. So after another t1, that is t0 plus 2t1, I will say reflected wave reaches BB prime. So therefore gamma 1 will be what? Gamma 1 will be Z0 minus Z1 divided by Z0 plus Z1. And if you notice, gamma 0 and gamma 1 are just opposites of each other. So this is nothing but minus gamma 0. Right? Now, this was the easy part. This was the easy part. So coming back to the time t equal to t0, some reflection happens with reflection coefficient gamma 0, and some part of it after reflection gets transmitted into this part of the line. And let us now define something called as transmission coefficient, that is T0. So I'll say over here, transmission coefficient T0. Likewise, when the backward wave comes, it undergoes a reflection gamma 1 and some of the wave goes back towards the source. Again, let us call that transmission coefficient as T1, that is over here. Now let us define the transmission coefficients. Reflection coefficients were easy to define, but transmission coefficient is not. Let us see how we can define this. Now, there are two transmission lines. One is the Z0 line, the other is the Z1 line. This is the point where x is 0. So therefore, let us write down the voltage and current equations as a function of x in the Z0 line, and in the Z1 line, let's write them as V1 of x and I1 of x. So, as per the solutions of the telegrapher's equations, this is what we will have. Plus some other constant V0 minus times e raised to j beta x. Note that this is the x-axis we are taking as convention, not the L-axis, which we normally do. And the I0 will be V0 plus by Z0 e raised to minus j beta x minus V0 minus divided by Z0 e raised to plus j beta x. Whereas for the Z1 line, we will have this, some V1 plus times e raised to minus j beta x plus V1 minus e raised to j beta x. Here it will be just the converse or just the extension of this, that is V1 plus by Z0 e raised to minus j beta x minus V1 minus by Z0 e raised to j beta x. Is it fine? Now, these two are the voltage and current in the Z0 line, and these two are the voltage and current in the Z1 line. Now, let us apply the boundary condition. That is the boundary between Z0 and Z1. What is that? That is x equal to 0. So in that case, what will be V0 of 0 and I0 of 0? V0 of 0 will be obtained when we put x as 0. That is V0 plus V0 minus. And I0 of 0 will be V0 plus minus V0 minus divided by Z0. Likewise, in the Z1 line, V1 of 0 will be V1 plus V1 minus. And I1 of 0 will be V1 plus minus V1 minus by Z0. So therefore, at the boundary, only at this point, these two should be equal and these two should be equal, because we are talking of a single point. The voltages on either side should be the same and the currents on either side should also be the same. This is the boundary condition. So having said this, let us define gamma 0. Gamma 0 is what? The reflection coefficient of the forward wave when it is trying to cross from the Z0 line into the Z1 line. So therefore, the reflection coefficient gamma 0 would be what? V0 minus divided by V0 plus. Likewise, gamma 1. Gamma 1 is the reflection coefficient of the backward wave when it is trying to travel from the Z1 line into the Z0 line. So in that case, what will be gamma 1? What will be gamma 1? Since it is the backward wave, we have to consider V1 plus and V1 minus. So in this case, the backward wave will be V1 plus and the forward wave will be V1 minus. So V1 plus wave is this one and V1 minus wave is this. But for the backward wave, this is the forward wave. So therefore, we have to do V1 plus divided by V1 minus. Now, what about T1? So, I'm sorry, T0. T0, that's a transmission coefficient when the wave is trying to go from the Z0 line into the Z1 line. So transmission coefficient is obtained when we take the voltage at the other side divided by the input voltage at the input side. So therefore, T0 will be V1 plus divided by, so this is V0 plus, I'm sorry, V1 plus divided by V0 plus, V0 minus. Make a note of this. V1 plus, V1 minus, V0 plus and V0 minus. So the transmission coefficient T0 when the wave is trying to go this side, cross the boundary, is V1 plus divided by V0 plus. So now from the boundary condition, we know that at this point the voltages on either side should be the same. That we saw that V0 plus V0 minus should be equal to V1 plus V1 minus. So if I now divide this equation by V0 plus, that means I will get 1 plus V0 minus divided by V0 plus equals V1 plus by V0 plus V1 minus by V0 plus. Now, this looks a very complicated equation. Let us again go back to our time information. Let us look at this time at t equal to t0. At t equal to t0, what is happening? So at t equal to t0, this wave is trying to cross into Z1 from Z0 for the first time. So now it does not know what the load is. So therefore, this line, the Z1 line, will not see any reflection. So at time t equal to t0, I can say that the reflected wave in the second line will not exist. Please note that the reflected wave will only exist after the wave hits the load at least once. It may exist in the Z0 line, but not in the Z1 line. At Z0, the reflection is taking place. So the reflected wave will start in the Z0 line, that is the V0 minus. This will start, but not V1 minus. So therefore, V1 minus can be made as 0 only at this time. So therefore, this equation becomes 1 plus V0 minus by V0 plus that equals V1 plus divided by V0 plus. What is this? This is gamma 0. And this is T0, the transmission coefficient. This is what we are seeing. So therefore, we already know what gamma 0 is. We already know what gamma 0 is. So let us put that. So we can say T0 is 1 plus gamma 0 is Z1 minus Z0 divided by Z1 plus Z0. And that comes out to be how much? That comes out to be 2Z1 divided by Z1 plus Z0. Right? So we shall pause at this point, having derived what is gamma 0 and using that finding out what is the transmission coefficient. We shall pause at this point and shall continue exactly from this point onwards in the next lecture. Thank you.